Hey everyone, I'm Nick, and welcome to a new short series on the C++ STL algorithms. So in this episode of the series, we're going to be looking at the different partitioning operations that we have available to us. So let's go ahead and get started, and we'll open up this partition.cpp. So we'll need to include the algorithm header here to use these partition operations. And we'll start out by just presenting a simple use case. So we'll have some STL container. In this case, we'll have a std array. A lot of times when we're using the STL algorithms, we're using them on STL containers. And in this case, we'll just have increasing numbers from 0 to 9. So we'll just go ahead and compile and run this. And so we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's say we want to partition these elements. So we want to say create a group of elements or a range of elements for which a condition is true and another range for which a condition is false. So that's essentially what partition does. It basically splits a range of elements into two groups, one of which for which a condition is true and the other for which the condition is false. So in our case, we'll be looking at sorting by odd and even. So here we have our first call to partition. So partition takes a pair of iterators. So this is just the pair to the range of elements that we want to partition. So in this case, it'll just be begin and end of A. And we pass in our actual condition that we want to check. So in this case, it's just a simple element mod 2 is equal to 0. So if an element, a number mod 2 is equal to 0, that means that it's even. And then any number that's odd, you do mod 2 on it, it should be equal to 1. Talking about integers, that is. So in this case, we'll go ahead and have, we'll partition these elements. And then what gets returned is just a predicate that corresponds to the end of the range of elements for which the partition is true. So let's go ahead and compile and run this and see how it looks. So before, we've just got our numbers counting up 0 to 9. Then after the partition, we have two groups of elements inside of our array. So we see the first half are all even numbers, so 0, 8, 2, 6, 4. And the after is all the odd numbers, 5, 3, 1, 7, or 5, 3, 7, 1, 9. And in this case, that midpoint that gets returned is the end of the range of elements for which the predicate was true. So you have to think about this end in terms of how we think about end in terms of, say, a vector or an array. So the end of, say, an array is 1 past the last element. So the end of the elements that are true would be 5, or the beginning of the elements that are false. And this is in the case of our partition, right? The end of our true elements in our partition. Okay, so that's a little bit on partition. So the next thing we have is this is partitioned and partition point. So we may have a container that's already partitioned, and we don't want to call partition again. And we may want to get that partition point, so the end of the range of elements for which the predicate was true. So the same thing that gets returned by partition, we may want to extract that even if we aren't calling partition. So we can use isPartition and partition point for those two operations. So both of these take the exact same arguments. So they take a begin and end iterator, and then they take some condition. So isPartition just returns a bool of whether or not this range is partitioned or not based upon this condition. And then partition point actually returns the end point of that partition, or rather the end of the first range of elements. Okay, so we can go ahead and compile and run this, and you see that partitioned, after we have already called partition, we see that partition returns true, or 1. And then this mid is equal to p, so p was returned by the partition point, mid got returned by partition, and you see they're both equal to each other, right? So it just gives us our partition point. Okay, so you may see another algorithm in terms of partition, which is this stable partition. So how does this compare with just, partition? So stable partition is the same as partition, except that it retains the relative ordering. So if we go back and we look at our original partition, we see that we got a range that was 0, 8, 2, 6, 4, and another that was 5, 3, 7, 1, 9. But that's a lot different than the relative ordering of elements in our original array. So the odd elements go in order of 0, 2, 4, 6, 8. And the odd go in order of 1, 3, 5, 7, 9. So what if we want to retain that order? Well, we can actually just use stable partition in this case. So with stable partition, it retains that relative ordering. So we do wind up with our partition of elements, but now the relative ordering is maintained. So now we get 0, 2, 4, 6, 8, and then 1, 3, 5, 7, 9 for odd elements. and it takes the exact same arguments. So it takes a begin and end pair of iterators. So it's just a range of elements we want to partition, and then our actual condition that we're going to check, except it retains that relative ordering. And again, it also returns an iterator, which is the end of that first range of elements for which the predicate was true. So then there's one more partition operation that we're going to cover today, which is this partition copy. So what if we get a range of elements that we don't want to modify their order, but we still want to partition it, right? Maybe we just want to partition it and save those partitions to a different place. So our true partition and our false partition. We can use partition copy. So partition copy is non-destructive, so it's not going to change the original array. So we'll go ahead and print that out. Except this time we pass in a begin iterator. So this is where we want to start filling the true range of our partition, and then and then an iterator where we want to start putting the elements that are false from our partition. So in this case, we're just using two separate arrays for our two output iterators, and then we've got our condition still. So again, this is not going to change the original array. It's just going to dump the true elements starting at some iterator and the false elements starting at a different iterator. So in this case, we'll just print out the original array. We show that it won't have changed, and then we'll print out those two, the true partition range, which is in this array now, and the false partition array, which is in, or false partition range, which is in this array now. And it also returns this pair right here. So the pair is very similar to the other returns for these different partitions, which is it's the end of a range of elements. So in this case, it's a pair of iterators. The first of which is an iterator to the end of the true range, and the second of which is the end of the false range. That's all this pair is. It just has two fields in it, a first and a second. Okay. Oops. So let's go ahead and save this, and we'll run it. And so you see that with partition copy, we don't change the original array. So this is after partition copy, and we just dump the true partition range into starting at one iterator, and the false partition range starting at a different iterator. All right, so that's gonna be the basics of using partition and all the different partition operations in the C++ STL. If you're interested, all this stuff can be found, of course, at the cppreference.com, so you can look up more in depth of how, say, partition works, and as well as some interesting examples down here. And as always, all this code that I wrote is available at github.com/coffeebeforearch. So here it's under repositories, C++ STL Algorithms, or CPP STL Algorithms, and partition.cpp. So feel free to download this, check this out. Let me know if you have any questions. And as always, I'm Nick, and I hope you have a nice day.